Hello, everyone. I'm Mary. So yeah, I work on NVK and Panfrost and a lot of things at Coraba since last year. And today we are going to talk about mesh shader on NVK. So first of all, what are mesh shaders? So mesh shaders are part of a new type of graphics pipeline with simplified stage. So you have the mesh shader stage that will generate all your geometry. And that's really closer to the actual compute model because you actually dispatch mesh workgroups. And you can also optionally have a dash shader that allow you to change the size of the subsequent mesh workgroup. So yeah, it's kind of simple. You get a pipeline like that. And let's say we want to do a simple point in the middle of the screen. Um, that will look like that. So you will first set the actual max vertices and max primitives. And inside the shader code, you are actually setting the number of primitives and vertices you are going to use. You set the actual attributes. You set the actual indices for each of those primitives, and that's it. It works like that. There is nice talks from XDC 2022 about that from Ricardo and also Timur on the AMD side, if you want more reference on that. So, okay, so mesh shader work like that. But like, I want to first mention how you do a draw on NVIDIA hardware in general, because that's going to be important here. So if you do a dump of the command stream on any draw you do on NVIDIA hardware, you'll find something like that. You will first find something that binds the resources from constant buffer attributes, textures, and stuff like that. Then it's going to bind all shader programs for vertices and like each of your stages, actually, and also disable anything that is not being part of your actual draw. Then it's going to set the draw control register with the topology information, the provoking vertex and instance code, I think. And then it's going to call draw vertex array in the command stream. So yeah, it's quite simple. And now I want to mention how it works in the actual shader. So the shader program is actually composed of a shader header and the shader code. So the shader header will contain all the attribute IO and some optimization flags here and there. The access to those attributes will be done with LD and LST instruction in the shader code, and each attribute actually have a unique ID. So if we take a simple vertex shader, you will get, for example, here the point size will be at 6C here with the IST store, and then the position will be after that. So it's quite simple. It's quite elegant, I would say, and it kind of maps to like the traditional way of like doing, the graphics pipeline, I would say. So it's kind of nice. So now let's talk about mesh shaders. So if we do the same exercise, but this time with actually a simple mesh shader, at that point, I'm going to reuse the actual shader from the start. Well, first of all, the command stream. If you dump the command stream, you will get something like that. First, it's going to bind the resources. Then it's going to bind the shader program stages from vertex, tessellation, and sometimes geometry. Then it's going to set the draw control register, and then it's going to call draw vertex array. Okay, so what's going on here? Well, actually, it's going to, when you are going to bind the actual shader stages, it's actually going to set the mesh control register to something, and then set some information about your actual mesh shader. So like everything that you actually define in the mesh shader around the max vertices, the max primitives, and also the topology. And if you actually look at the actual draw part, you will get something like that. So the first thing to note is that the draw control register is going to ignore the actual instance index. And then the second thing to note is that the draw vertex array is actually going to be called with the workgroup size. So what is going on here is that we are actually driving a draw with the input assembler without any inputs, except the vertex ID actually, but let's say without any inputs. So in reality, your pipeline will look like something like that. So if you have a task shader, then the task shader is going to be the vertex shader. And then the mesh shader is going to be the tessellation evaluation shader. And if you don't have a task shader, it's going to actually use the vertex stage for the mesh shader. So that's nice. Now we know how to actually dispatch mesh shaders. But now let's talk about the actual shader code. So I took the actual example from the start, and I can show you like the actual disassembly here. So the first thing to note is that we don't have any LD or AST instruction here. It's using a new shiny instruction, ASB write. So the first thing that you can like actually guess is that the primitive count is stored at offset 0. Yes, offset 0. It's actually written 3, but it's actually storing from 3 to 1, 0 from that space specifically for some reason. Then you can also see that the primitive indices will be after that with that store. And then we have the attributes that are here. So the thing to note here is that we are actually writing directly to the primitive engine internal buffer. So the primitive counts and the primitive indices are stored in one specific space, and then you have the attributes in another space. That attribute space is a bit of madness, I would say, because it's entirely dynamic. It's group, like each actual attribute is grouped with 32 values of the same kind of attributes, so grouped by vertices or per primitives. And the order is defined with the actual shader I/O. So like, for example, if we have the point size that is actually defined and also the position, like position, all the position, then we'll always will have the actual point size and then the position. And if we don't set the actual point size, for example, we will start with the actual position X. And yeah, all that layout actually repeats if you have more than 32 vertices. So yeah, it's really complex. It took me quite a while to figure out. There is here a little example of how that will look like with our shader here if we had, like, for example, more than like 32 vertices. But it gets worse because we have per primitives attributes too. And in that case, the same kind of layout and rule apply, but this time it's going to be after all of that. And the shader header that is going to contain all the attribute I/O information is the geometry stage. And the geometry stage is actually configured to actually pass through all those values directly. So yeah, that's a lot. I implemented all of that, and now I can talk about like, well, what is the state of all of that? So what is the current state? Last week I did like a little, digging about some demos from Chronos Group. So we have the little triangle working. That's great. We have the double FPS compared to NVIDIA for some reason. I don't know why, but I would like that. But now let's talk about like just the CTS. So if you run the CTS currently with the merge request I opened some time ago, you will get those results. So like those are the results from last week. It's quite close, but quite far actually, because I currently disable task shaders because task shaders are kind of not in love with mesh shaders. I have multiple issues with them, ranging from the local invocation index being wrong and different, depending if you have mesh and task present. The mesh shader queries are not implemented yet because I need to actually store that in shaders or actually in the command stream, like do that in command stream. And there's probably more here, but that's something for a bit later. The other thing I want to mention is that we don't have real shared memory with the graphics pipeline on the hardware. Because of all of that, we are using the actual internal space to store the shared memory. And that means I need to emulate atomics because I don't have any ways to do atomics. So I'm using the uniform atomics pass that does a lot of it, but I still need to handle the atomic exchange, for example, intrinsic. The really elephant in the room now is around the invocation. Because we are running on the actual graphics pipeline, we only have 32 local invocation. The spec actually require 128 of them. And so NVIDIA actually implement that by emulating invocation. So like one hardware invocation can be up to 4 actual invocation in the shader. That's non-trivial to actually like create, I would say. And I had a lot of trouble trying to get that in here to fit. So yeah, I think that's it. I may have spoke a bit fast. Sorry about that. Any question?
If nobody else is going to go, I'm just going to say that you were very much understandable.
Okay, thank you.
What exactly is missing for task shaders? Sorry.
Yeah.
So what exactly is missing for task shaders?
Well, task shaders should be working. The thing is, because of all the local invocation mess, I didn't do much testing here, and like all of the faults I'm having right now are probably related to me not handling correctly, having more invocation. So like right now, the way I handle invocation is by just grabbing the shaders and executing that up to 4 times without while ignoring all barriers for now. So like that's completely wrong. Somehow that passed like a lot of the CTS in mesh shader mode only. But yeah, I know that like the global invocation index is kind of broken, but like shared memory and task payload actually work. Like I know that interaction on both stage work, like simple example work fine. I'm just not sure what is currently broken. Probably I need to set some registers for like unlocking probably more shared memory if needed, like more ASB space for that. But like because of all the local invocation thing, and because I was doing most of my testing with CTS, it's kind of hard to get, make a sense of what is broken on both. Yeah.
So, hey, little dumb question, but
Yeah.
so the disassembly code you were showing as part of the shader program, those are in NVIDIA's instruction, like
Yeah.
not whatever OS assembly would be, correct?
Yeah,
Okay.
it's actually using the actual disassembler from CUDA that ship with CUDA.
Thank you.
Yeah. And while I'm at it, I can mention that like all the command stream that I showed to are using one of the tool I have made a while ago that allow you to basically hook inside the process the actual doorbell that handle the user submission. And so we basically can dump anything on the command stream that way by just loading a library and getting it that way. Yeah.
For the, you mentioned handling of the greater than 32 invocation mesh shaders that NVIDIA does something to put them all into 32. Is that just like a loop over the four invocations or something?
So like the way I'm currently doing it, well, the way I'm currently doing it is by basically grabbing the entry points, making it like a new function with an argument that is the actual local invocation index, and then calling that up to 4 times, and then like just inlining that. That doesn't, that's not correct because you need to respect barriers, but like respecting barriers, like emulating that properly is kind of complicated, I would say. We had some discussion with Faith around that, and I tried to implement that a lot. but I was like having a lot of trouble trying to extract part of the neologic while like staying inside the actual limitation of, you know, cutting a part of the logic and like pasting it somewhere else. Like it's, yeah, it's kind of hard, I would say. I think I have a branch somewhere.
Can I have a general question? Like when you're looking at the like reversing the NVIDIA behavior, can you see their like instruction stream, command stream, and how is that different from the NVK and like method drivers in general?
Like seeing like how to do this, like how to grab the stream and stuff.
Not exactly how to grab it, but like example, you're running some test, right, for
Yeah.
this behavior on an official driver. Can you see like everything that the driver is doing, like all the commands, all the like shader stuff? And
so if you, let's say I want to debug, for example, the difference between a CTS test I have and NVIDIA driver, I would say, I have like I have NVHooks, that is my library to do dumping of command stream. So if you preload that in the process, it's going to actually dump all the command stream somewhere. For the actual shader part, though, it needs another thing that that is like a layer, like a Vulkan layer that hijack the pipeline cache and then dump the pipeline cache, and then we extract that, like we extract the shader from the pipeline cache. We can also do that for if you have shader objects. I also have a tool that is able to grab the blob and be able to extract the actual like header encode of the shader that way. So like it's not really like a one tool handling everything. Like I cannot do that like simply, but like I have the script that handle both and then extract everything when I run, for example, the test of the CTS or any demo application, to be honest. But yeah, does that respond to the question?
yeah, thank you. That's interesting. And like the second part of the question is how NVIDIA behavior is different from NVK. Like, is there substantial differences in how things are done?
I mean, that's kind of well, from the top of my head, right now we don't use the multi-view hardware, I would say, for example. We don't use the same way to do draws. Like I did show the actual draw control register and the vertex array thing, but like there is another way that is the old way that we still use. I think I have a merge request open. But like, yeah, there is like a lot of difference here and there because we don't know any, like all the part of the hardware. And so, yeah, it really depends, to be honest. And to be honest, like, for example, for the local invocation thing, I'm more and more thinking about doing it with a compute shader and then handling it that way, because I think we still have limitation on the primitive counts that we can emit per mesh stage. So yeah,
So it's a bit different. Okay.
Yeah, it's a bit like, I mean, it's kind of different. Yeah.
Got it. Thank you.